defect which we wrote here is local action. How does this local action work? How does it exist? So what actually occurs is that this zinc rod, or let's just say in general, I'll tell you that there is nothing on this earth that is pure, totally pure, 100%. It is very difficult for you to say, oh, this thing is 100% pure, it's clean. So also the zinc rod here. The zinc rod is not 100% pure because it contains some form of impurities, which can be carbon and different form of impurities. Now, that is what breaks down the zinc rod. The zinc rod begins to deteriorate, begins to diminish, begins to destroy, and when the zinc rod continuously destroys or begins to lose its capacity, you observe that there is a problem and the cell does not perform well, and hydrogen gases are usually generated, and almost the same thing as polarization. So that's one of the challenges that occurs in local action. So local action occurs because the zinc rod or the zinc plate is filled with impurities. So when the zinc plate is filled with impurities, how do you solve the problem? So it keeps diminishing, and there's no current or EMF generated. So is that how you want your cell to be? No. So what occurs is, as a result of this, we now have to solve it. To solve the problem, we tend to use a process called amalgamation. So amalgamation. And how do you amalgamate? You use mercury, Hg. Just come and say, oh, this is our zinc rod. This is the zinc rod. Just come here and rub some pieces of mercury on the zinc rod. And this zinc rod that usually has this issue of deterioration and dropping and issues and all that, you just rub it on it. And when you rub it on it, what happens? The zinc rod begins to function very well again, and this local action has been solved immediately. So to solve this using amalgamation, we rub the zinc rod or plates with mercury, and this has solved the issue immediately. So when you rub the zinc rod with mercury, you observe that local action has been solved. You take note that resistance is an opposition to the flow of currents. That's one aspect. Then you also take note that resistors can be arranged in series or in parallel. So in series, when we talk about in series, we say that ROT equal to RO1 plus RO2 plus RO3. Then for parallel, in parallel we have 1 over ROT equal to 1 over RO1 plus 1 over RO2 plus 1 over RO3. So we take note that ROT is equal to RO1 plus RO2 plus RO3. Then in parallel we have that 1 over ROT equal to 1 over RO1 plus 1 over RO2 plus 1 over RO3. So we also take note that RO is equal to L over A, where rho is resistivity, L is length, then A is area. And this aspect, rho is equal to resistance. Then you take note that this area is pi rho square, because whenever we're talking about resistance in a wire, we're actually dealing with a circle or a cylinder. So formula is what? Pi rho square, which is A as this. Then the unit must be in meters for length. The unit must be in meters for length. Now just told you about all these aspects, told you about all these resistance in series, parallel, and all that. Now, I will also tell you that I gave you something called Ohm's law. Ohm's law. Now, Ohm's law states that the voltage is directly proportional to the current, where temperature and other effects are constant. So temperature etc is constant. Now from this we can now say that V equal to I R, where it's supposed to be IK or KI, but now that K is the resistance. Resistance is the constant here. So resistance is the what? The constant in this aspect. Now and resistance is our constant, so we have V equal to IRO. Then if we have V equal to IRO, we also need to relate all our formulas together. So we have the first formula, which is W equal to QV. We have the next one, which is V equal to IRO. Then we have the next one, which is Q equal to IT. Now I'm going to use these formulas now. These three formulas is number 1, number 2, is number 3. Now if we have that W equal to QV, let's come here and say Q equal to IT in this W. So W, first of all, is work. Let me explain. W is work. V equal to voltage. Q equal to charge, electric charge. I equal to current. T equal to time. R equal to resistance. Now with what we have here, we can now say that Q equal to this Q here. So we can just say that W equal to IT times V, which is equal to IVT. Now if we have this W equal to IVT, then also we know that V equal to IR. So if V equal to IR here, we have that I times IR times T. So W equal to I square RT. So it's our first equation. That's our second equation. Then we also know that if V equal to IR, we can also write that V over R equal to I. So we can come here, let's replace this I here with V. So we have that W equal to IVT before. So we'll just come here and replace this I with V over R. So V over R times V times T. And this will give us V times V, which is V square over ROT, which is our equation 3. So you take note that we have 3 equations, that W is equal to IVT equal to V square T over RO is equal to I square ROT. So these are our 3 equations. Then also you take note that power is equal to work done over time taken. So the work done now we already calculated IVT. So IVT over T, V square T over RO T equal to I square ROT over T. T here 1, 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 T here 1. So we have that power is equal to IV is equal to V square over RO is equal to I square RO. You know that power is equal to IV. Okay. You know that power is equal to IV. Power is equal to V square over RO. Power is equal to I square RO. So W equal to IVT equal to V square T over RO is equal to I square ROT. So you take note of all these things. Now, how many factors affect electrical resistance? So the factors that affect resistance, include the following. 1, the length of conductor. The second one is the area of conductor. Then the next one is the temperature of conductor. Then finally we have the type of substance or material. So there are 4 things that can affect electrical resistance. So one of them is the length of conductor, the area of conductor, the temperature of conductor, and the type of substance or material involved. So you can have the type of conductor, the strength of conductor, that's the area of conductor, the temperature of conductor, then the type of substance or material involved.